Sige. Hi, I'm Hadi.
Hi, I'm Isma. Hi, my name is Aina. Hi, I am Shara.
Chemical EOR, which is the enhanced oil recovery method, serves as the tertiary recovery method, implemented once the first two stages have been fully leveraged.
EOR is necessary because conventional extraction methods typically leave 60–80% of oil trapped within reservoirs. Primary recovery, which relies on natural reservoir pressure, typically only extracts 10 to 15% of the original oil in place. Secondary recovery methods like water flooding may increase this recovery to 20–40%. This limited extraction efficiency means significant oil resources remain trapped underground. These remaining oil reserves amount to billions of barrels of potential energy that would otherwise go unused. By contrast, EOR techniques can access much of this remaining oil to meet global energy demands. It significantly increases the amount of extractable oil from existing reservoirs, typically enabling the recovery of 30 to 60% of the original oil in place. This substantial improvement unlocks billions of additional barrels of oil production globally. Besides, many oil fields considered depleted under conventional recovery methods contain significant untapped potential. EOR transforms these seemingly exhausted assets into valuable production centers once again. The importance of EOR grows as easily accessible oil reserves continue to deplete worldwide. It's a critical approach for energy companies seeking to maximize production from existing fields rather than relying solely on new discoveries. EOR techniques encompass a range of processes developed to significantly increase oil production beyond conventional recovery methods. Thermal EOR methods involve introducing heat into the reservoir to reduce crude oil viscosity, thereby improving its flow toward production wells. These techniques are especially effective for heavy oil and bitumen reservoirs, where high viscosity severely restricts oil mobility. Common thermal EOR methods include steam injection, in situ combustion, and electrical heating. Gas injection EOR techniques enhance oil recovery by injecting gases that improve oil mobility through mechanisms such as oil swelling, viscosity reduction, and pressure maintenance. Depending on reservoir pressure and fluid properties, these methods may be miscible or immiscible. Gas injection EOR is generally more effective in medium to light oil reservoirs, with commonly used gases including carbon dioxide, nitrogen, and hydrocarbon gases. In contrast, chemical EOR techniques, particularly surfactant-based methods, directly target the fundamental forces that trap oil within reservoir rock. Chemical EOR involves injecting chemicals to alter the properties of the oil-water rock system, making it highly versatile and applicable across a wide range of reservoir conditions. Surfactant flooding plays a critical role in chemical EOR by reducing the interfacial tension between oil and water, allowing trapped oil droplets to be mobilized and displaced more easily. This reduction in interfacial tension significantly weakens the capillary forces that hold oil within pore spaces. To further enhance recovery efficiency, surfactants are often combined with polymers in surfactant polymer (SP) flooding. In this approach, surfactants improve oil mobilization, while polymers increase the viscosity of the injected water, improving sweep efficiency and reducing early water breakthrough. Through this combined mechanism, surfactant-based chemical EOR enables the effective displacement of residual oil that cannot be recovered using thermal or gas injection methods alone, making it a key technology for maximizing oil recovery from mature and complex reservoirs.
In research conducted by Jia and Kong, 2025, the article explained how surfactants and nanomaterials work together to overcome capillary forces and maximize oil recovery through three primary mechanisms. The first mechanism is through interfacial tension, IFT, reduction. Surfactants are amphiphilic molecules with a hydrophilic head and a lipophilic tail. They migrate to the oil-water interface, reducing the cohesive forces that trap oil droplets. When combined with nanoparticles, this effect is amplified, reaching ultra-low IFT levels. This allows trapped oil to deform and flow. The second mechanism is mitigation of surfactant adsorption. A major challenge in EOR is the loss of surfactants due to their tendency to stick to reservoir rock. Nanoparticles act as sacrificial agents by competitively adsorbing onto the rock surface first. This prevents surfactant loss, ensuring more of the chemical reaches the oil bank to facilitate recovery. The last mechanism is wettability alteration. Surfactants alter the rock surface from oil wet, where oil clings to the stone, to water wet. Nanoparticles further this by creating structural disjoining pressure. As nanoparticles accumulate in the wedge between oil and rock, they form organized layers that physically peel the oil droplet away, allowing it to be swept toward production wells.
After water flooding, oil remains trapped in oil-wet carbonate pores. Injected surfactant reaches the oil-water interface, lowering interfacial tension. Wettability shifts from oil wet to water wet. Detached droplets merge and move toward the well. Polymer improves sweep, reducing channeling. Result: lower residual oil and higher recovery.
An example of the real-life applications of surfactants in EOR is in the Sabaria Maudud Sama Reservoir, which is the largest carbonate reservoir in northern Kuwait. The reservoir still contains a high initial oil saturation of approximately 80%, and the reservoir temperature is around 78 degrees Celsius. Due to the large amount of remaining oil and the limitations of conventional recovery methods, enhanced oil recovery was required to meet production targets. During the planning stage for the EOR, chemical EOR was selected. It was considered compared to CO2 injection, which was found to be unsuitable due to the large volume of CO2 required and high surface facility demands. In preparing the surfactant system required, the formulation was modified from ASP to SP flooding, consisting only of surfactant and polymer. This is because the analysis of Sama oil samples showed a very low total acid number, around 0.05, hence the oil had little tendency to react with alkali to generate in situ soap. The surfactant system used included 0.65 weight percent C2E8 25PO 45EO carboxylate and 0.85 weight percent internal olefin sulfonate. FP3330 polymer was added to increase solution viscosity and improve mobility control. Additionally, 1% Na4EDTA was included to chelate iron and alter wettability from oil wet to water wet conditions. Further optimization was carried out by varying surfactant and polymer concentrations and testing the addition of alkali using soda ash.
Initial tests reduced oil saturation by 45 to 55%, but were limited by reservoir conditions and design issues. After improvement, oil saturation dropped to about 0.06% saturation, confirming highly effective oil removal in the Sama reservoir. The technique was hence in process to be approved by Kuwait Oil Company. Despite their effectiveness, surfactants in enhanced oil recovery EOR face several challenges. Firstly, synthetic petroleum-based surfactants are toxic and can harm the environment. Secondly, most surfactants are unstable at high temperature at above 60 degrees Celsius and high salinity, which reduces their performance in harsh reservoir conditions. There are few advancements in EOR to combat the challenges. Firstly, is using natural and green surfactants that are biodegradable, renewable, and less toxic. Examples include surfactants derived from tarragon, tenacetum plants, and flaxseed oil. These natural surfactants are equally efficient, reducing oil interfacial tension and improve oil recovery. Another improvement is the use of nanoparticles such as silica, magnetite, and graphene oxide. These nanoparticles help increase surfactant stability, reduce adsorption losses, and enhance performance under high temperature and high salinity conditions, leading to more efficient oil recovery
Surfactants are changing EOR. They lower interfacial tension. They flip wettability. Polymers improve sweep and flow conformance. They push what water misses. Trapped oil becomes mobile. Then it moves to the wellbore. Result: much lower residual oil saturation and higher recovery than water flooding. Clean chemistry, better recovery.